A truly rigid stick would be a faster-than-light telephone. Push here, the far end moves now. Sounds harmless until you ask what now even means in relativity. So why does a table feel perfectly solid if perfect rigidity is forbidden? Pick up a metal rod or a broom handle, hold one end in your hand, and tap the other end against the floor. You feel it immediately. Not because the far end decided to move and told your hand out of politeness. You feel it because something physical traveled through the rod and reached you. And this is where the everyday idea of a solid object quietly cheats. In daily life, solid means one piece. Push one end, the other end responds. Instant. Like the object is a single connected decision. That's how our brains picture it. A rigid thing. Physics lets you use that picture in a lot of calculations. Engineers use it. Intro mechanics uses it. It's a terrific approximation, but it's an approximation of something that cannot exist in the real universe. Because if an object were truly rigid, perfectly rigid, then a push here would cause a motion there with no delay at all. And that single phrase, no delay at all, is not a detail, it's a law-breaking machine. No delay at all means information traveled across the object instantly. And instantly is just another way of saying faster than light. So the problem isn't that real materials are a little squishy. The problem is deeper. Perfect stiffness would let you send signals with infinite speed. It would let you coordinate distant parts of matter without time. It would tear a hole in relativity. Let's pin down what we mean, because words like solid and rigid are sloppy. A perfectly rigid object would have this property. The distance between any 2 points in it is absolutely fixed, no matter what you do: push, pull, twist, accelerate. No compression, no stretching, no internal delay. It moves like a single geometric shape. Now imagine the simplest possible test. You have a long rod, 1 kilometer long, just to make the delay big enough to notice. You put a tiny marker at the far end. You push the near end forward by 1 millimeter. Question: when does the far end start to move? Your intuition says right away, because it's one piece. But what does right away actually mean? It means the far end must somehow know that you pushed. How does it know? There are only a few honest answers. 1. It knows because something traveled through the rod. 2. It knows because the rod is magical. 3. It knows because the universe allows instantaneous influence. Physics rejects 2 on principle, and it rejects 3 because of everything we've learned about cause and effect since Einstein. So it must be 1. Something travels through the rod. What is that something? In everyday language we call it a jolt. In physics we call it a disturbance. In material science it's a stress wave. In plain terms, a little region of compression that moves along the rod. A push does not move the whole rod. It moves the first layer of atoms. Those atoms shove the next layer. They shove the next. A relay race. It's always a relay race. And the speed of that relay is not infinite. It's basically the speed of sound in the material. Steel, a few kilometers per second. Wood, less. Rubber, much less. So for a 1 kilometer steel rod, the news that you pushed arrives at the far end after roughly a fraction of a second. Not long, but not zero. And here comes the first uncomfortable realization. When you push a rod, there is a moment, tiny but real, where the near end is moving, and the far end is still doing absolutely nothing. Meaning the rod is for that moment, not a single object in the way you pictured it. It's a chain of interactions unfolding in time. Now you might say, fine, real rods aren't perfect, but I can imagine an ideal rod, perfectly rigid in principle. That's where the word impossible enters. Because if you allow perfect rigidity, even as a theoretical possibility, you've allowed a superpower, instantaneous communication through matter. You could send a signal by pushing one end and watching the other end respond immediately. Not with a laser, not with a radio wave, just with a stick. And you could do it across any distance, 10 kilometers, 1,000,000 kilometers, across the solar system. If you could build the stick, the length doesn't matter because you've built instant. Relativity says you can't build instant. Not for signals, not for information, not for cause and effect. So relativity doesn't merely suggest that perfectly rigid objects are unlikely. It forbids them. But wait, this sounds like it contradicts something you've heard. Nothing can go faster than light. Yet sound in a solid is much slower than light. So what's the big drama? The drama is this. Rigidity is not fast sound. Rigidity is infinite sound. Rigidity is the statement that mechanical influence has no travel time. And the moment you demand that, you are demanding infinite propagation speed. Even worse, perfect rigidity would let you do weird things with acceleration. Imagine a rigid rod, again 1 kilometer long, floating in space. You grab one end and start accelerating it. If the rod is perfectly rigid, the other end must accelerate at the same time with the same pattern, because the rod's length cannot change and it must remain one piece. So by wiggling your end, you control the motion of the far end instantly. That's not just communication, that's remote control without delay. And if you can do that, you can create cause and effect paradoxes when different observers disagree about which event happened first. That's not philosophy, that's the actual content of special relativity. If signals could travel faster than light, different reference frames can reorder causes and effects. So the universe has to choose, either allow perfectly rigid bodies or keep causality sane. It chose causality. Now here's another layer people miss. Even the speed of sound in the material is not a fundamental speed limit. It comes from something deeper. Sound is not a separate thing. It's atoms and electromagnetic forces. Atoms sit in a lattice. They attract and repel each other through the electromagnetic interaction. When you compress one region, you slightly change the spacing. That changes the forces. Neighboring atoms respond. That response is what we call elasticity. So the maximum speed at which a mechanical disturbance travels is tied to how quickly those interatomic forces can do their job, how quickly they can pull, push, restore. An electromagnetic influence itself doesn't propagate instantly either. Changes in the electromagnetic field propagate at the speed of light. So even in the most optimistic fantasy materials, stronger than steel, perfect crystal, whatever, the ultimate limit is still lurking. No influence in nature transmits faster than c-per. That means there is no route to perfect rigidity. You can't cheat it with better engineering because the barrier isn't our technology, it's the structure of interactions in space-time. Now, if you're thinking clearly, another objection pops up. Hold on. If rigid objects are impossible, why does a table feel rigid? Why does a wall stop me? Why does a diamond scratch glass? Good, because this is exactly the trap the word impossible sets. Impossible doesn't mean soft like a sponge. It means not infinite. A wall can be extremely stiff. It can respond very fast. It can feel to your slow nervous system like an instant unified reaction. But fast is not instant. Large is not infinite. Strong is not absolute. Your hand is full of senses that fire on millisecond timescales. Your brain stitches reality into a continuous story with a certain frame rate. If the delay in the rod is microseconds, you will swear it was immediate. Your nervous system literally cannot tell the difference. Physics can. And the distinction matters because when you push the idea to extremes, very long objects, very fast impacts, very precise timing, the almost rigid story breaks, and the real story shows through. Signals, waves, finite speed, delay. So the problem we're defining is not why are solids strong. The problem is, what is solidity really? If the universe forbids a truly rigid thing, what does it mean that the most familiar objects in your life, tables, rocks, bones, owe their apparent one-pieceness to a message traveling through them? And if that message has a speed limit, what does that do to the way forces work, collisions work, and even the way you should picture matter? Because the next step is going to sound almost insulting to common sense. When you hit a rigid-looking object, you're not pushing the object. You're launching a wave inside it. And once you see that, a lot of everyday physics stops being boring. It becomes a timed process, with delays, reflections, ringing, and a built-in speed limit inside every so-called solid thing you've ever trusted. And once you see that, you start noticing waves everywhere. Hit a bell, that's obvious, it rings, vibrations. But hit a non-ringing object like a block of steel with a hammer, you think it just moves, or it just stops the hammer. No. For a brief moment, the steel near the impact compresses. The atoms get shoved closer than they like to be. That compression is not a static thing, it's a traveling pattern, a pulse, like a traffic jam that moves backward along a highway even though the cars move forward. The atoms don't travel from one end to the other, the disturbance travels. Now here's the key point that wrecks the rigid body picture. During the first instant of a collision, most of the object doesn't even know it's being hit. If you smack the end of a long rod, only a short region near the end feels the stress at first. The rest is still in its previous state, quiet, unbothered, minding its own business in space-time. So when you say the rod is pushed, what you really mean is a stress wave has been launched, and as it sweeps through, different parts of the rod begin to move. That's not poetic, that's literally how impact works. You can even do a thought experiment that makes it impossible to hide. Imagine a rod floating in space and you hit one end with a tiny impulse. If the rod were perfectly rigid, the whole rod would instantly acquire the new velocity. Every atom would agree at the same time, we're moving now. But in a real rod, at first only the near end moves. For a while the rod is partly moving, partly not. That means the rod is temporarily compressed. It stores energy in that compression like a spring. Then the compressed region moves down the rod. When it reaches the far end, that end finally begins to move, and depending on what the far end is doing, free, clamped, attached to a mass, the wave reflects, inverts, rings, and you can get oscillations. So a solid object is not a rigid chunk, it's a medium that supports waves. Now you might be thinking, okay, fine, but it's still very fast. So why call rigid objects impossible? This sounds like a nitpick. Good, let's sharpen it until it hurts. Suppose I want a perfectly rigid rod for one practical reason. I want to use it as a communication device. I'm on one end, you're on the other, we're far apart. I push once for yes, twice for no. If the rod were rigid, you'd feel it instantly, across any distance. That would be a faster-than-light telephone made of metal, and the reason that's so dangerous is that faster than light is not just faster, it changes the structure of time. In relativity, two observers moving relative to each other disagree on what events are simultaneous. That's not an opinion, that's a consequence of how light behaves and how we measure time with signals. So if you allow a signal to go faster than light, you open a door. There exist frames of motion where the effect happens before the cause. Not it seems like it. It actually flips in the math. You can build loops where you send a message and receive a reply before you sent the original. You can make contradictions. You can break causality. Relativity survives because nature refuses to give you instantaneous influence. And this is why perfect rigidity is not merely very stiff. It's causality violating stiff. So the universe doesn't allow it. Full stop. Now let's bring it back down to earth and make it tactile again. Why do you feel a table is hard? Because when you push your hand into the table, the atoms in your hand approach the atoms in the table. And when they get close, really close, the electromagnetic forces between electrons become violently repulsive. Not because electrons are little hard balls. Because of quantum mechanics, electrons are described by wave functions. And the Pauli exclusion principle makes it energetically expensive to cram them into the same quantum state. That repulsion is what you interpret as solid, but that repulsion is still a physical interaction, and when you press, you create a rearrangement of forces that propagates into the material. The table slightly compresses, the floor slightly compresses, the earth slightly compresses. Yes, the earth. If you press on a table leg, the stress goes down into the ground as a wave and then settles into a new static pattern. That's why buildings can transmit vibrations. That's why you can hear footsteps through a floor. That's why earthquakes exist as traveling elastic waves through rock. The rigid table is rock behaving like a spring, a very stiff spring. Now watch what happens if we push this idea into a famous rigid scenario. Newton's cradle. You've seen it, 5 identical steel balls hanging. Lift one ball, let it hit the row. One ball on the far end flies out. It looks like instant action through a rigid line of spheres, like momentum teleported. But inside those balls, the same thing happens, compression. When the first ball hits the second, the contact region squashes slightly. A stress wave enters the second ball. It reaches the far side of that ball, and then transmits into the next contact. The push walks down the line as a sequence of deformations and waves. If you had a high-speed camera and sensitive force sensors, you'd see delays and oscillations. You'd see the balls ring with tiny vibrations. The clean instant exchange is an illusion created by stiffness and symmetry. That's the general theme. Rigidity is a story we tell when we're too slow to see the inside. Now there's an even nastier place this shows up, rotation. Imagine a perfectly rigid disc like a record spinning. If you could grab the rim and jerk it, the whole disc would have to respond instantly to maintain rigidity. Every radius would have to coordinate at once, but coordination means signals, and signals have speed limits. So in real rotating objects, changes in rotation propagate through the material as torsional waves. That's why shafts twist under torque. That's why a long drive shaft can wind up. That's why you can snap something by twisting quickly. One part starts turning before the other part even knows it should. And in relativity, rotation is a minefield because different parts of a spinning disk have different velocities, and you can't make the whole thing born rigid in the naive sense. The geometry itself fights you, but we don't even need the full relativistic machinery to get the punchline. Here's a simpler one. Imagine the world's longest train, 1,000 kilometers long. Perfectly coupled cars. You're at the front with the engine. You start pulling. Does the last car start moving at the same time? Of course not. The couplers stretch. The tension wave moves backward along the train at a finite speed. That's why trains start with clanks and jolts. That's why engineers worry about run-in and run-out forces. The train behaves like a slinky made of steel. Now replace train couplers with chemical bonds. Same idea, different scale. And this is where a lot of textbook mechanics quietly sweeps reality under the rug. When you learn about rigid bodies, You learn that a force applied at one point produces a motion of the whole object, with a neat torque, a neat acceleration, a neat rotation. It works because you're assuming the internal forces adjust instantly to enforce the constraints of rigidity. But the real enforcement is a communication process. It's atoms pulling on atoms, and that pull can only influence neighbors after a delay. So the constraint isn't a commandment. It's an approximation that becomes accurate when the object is small, the material is stiff, and the timescale of your motion is slow compared to the time it takes waves to cross the object. Slow compared to the crossing time. That's the condition. And suddenly you can make a hard object feel very non-rigid by changing only one thing: speed. Tap a piece of glass gently, it's rigid. Hit it fast, it shatters. Not because force got bigger in some vague way, but because the stress wave didn't have time to spread out. The local stress exceeded the material's strength before the rest of the object could share the load. Rigidity isn't just a material property. It's a race between your timescale and the signal speed inside matter. And once you frame it as a race, the everyday idea of a single solid thing starts to dissolve. Because what you're really holding is a democratic system of atoms with a finite voting speed. You push here, the nearby atoms vote first, the others vote later. No object gets to be a dictator that commands instant unity across space. Not in this universe. Not in this universe. And once you accept that, the word solid stops meaning what you thought it meant. It stops being a statement about a thing. It becomes a statement about timing. A solid object is one where, for the situations you care about, the internal message travels fast enough that you can pretend it's instant. That's all. The table doesn't resist you because it's a mystical hard slab. It resists because the electrons in the atoms don't allow easy overlap, and because the pattern of forces created by your push spreads through the material quickly enough that your hand meets a coordinated response. Coordinated, not instantaneous. Now take that same table and ask a cruel question. How long does it take the far corner of the table to know I pressed here? Not how long until the table moves noticeably, how long until any physical influence reaches there. The answer is roughly the size of the table divided by the speed of sound in wood, milliseconds. And to a nervous system that's working with tens of milliseconds, it feels like magic. Like the table is one piece. Your sense of rigidity is basically a perceptual compression algorithm. It throws away the delay because it's below your resolution. Physics refuses to throw it away, because the moment you build a longer object, or you act faster, or you demand precision, the delay stops being negligible and becomes the whole story. That's why a long bridge sways. That's why skyscrapers move in the wind. That's why an earthquake can make a city shake seconds after the ground ruptures somewhere else. That's why a guitar string transmits vibration, why a bat feels the ball, why armor works, why helmets crack, why a whip can snap. A whip is actually a perfect little demonstration of non-rigidity. You put in a motion at the handle, and the shape change runs down the length. The tip reaches enormous speed, sometimes even exceeding the speed of sound in air, creating a shock wave. The crack, that entire effect is only possible because the whip is not rigid. Rigidity would kill the whip, and now you can see the deeper statement hiding behind the everyday one. The universe does not let you enforce constraints instantly across space. It doesn't let you tie distant points together with an invisible immediate must. Everything is local. Everything is neighbor to neighbor, even in a solid. Now there's a temptation here to say, so what? Fine. Perfect rigidity is forbidden, but we never needed it anyway. But you did need it, mentally, because the idea of a perfectly rigid object is one of the oldest crutches in human intuition. It's the idea that matter can be a single unified thing, that the world can contain objects that simply are what they are, independent of time. And physics keeps doing this to us. It takes our comfortable nouns and turns them into verbs. A solid is not a thing. It's a process of forces holding patterns stable with finite response times. A push is not an action that transfers instantly through a body. It's a traveling disturbance. A collision is not an instantaneous event. It's an interaction that unfolds over a contact time, with waves entering and leaving, energy stored and released. Even rest is not a deep fact. It's a relation between reference frames. So what's left of the object? A pattern, a structured self-maintaining arrangement of fields and particles that responds to changes with a finite speed. That's the honest picture. And this is where relativity quietly becomes personal, because it's not just about spaceships and cosmic clocks. It's about your hand on a doorknob. Relativity says there is no universal now, no global simultaneity that the whole universe agrees on. Perfect rigidity would require a universal now inside the object, It would require the object to have its own private notion of simultaneity. This push here and that motion there happen at the same time, but same time across distance is exactly what relativity refuses to make absolute. The universe doesn't hand you that. You have to define it with signals, and signals have a speed limit. So a perfectly rigid object isn't just a super strong material, it's a claim that you can stitch space together with an absolute simultaneity. And that's why physics says no. The limit isn't weakness, the limit is the structure of spacetime. Now bring your mind back to that simple rod again. When you push it, you're not moving the rod, you're sending a message through it, and the rod is an obedient messenger, but it's not allowed to run faster than nature permits. It runs at the speed set by the material's elasticity and density, by how stiff the bonds are, and how much mass has to be moved for the disturbance to pass along. And those bonds underneath are electromagnetic, and changes in electromagnetic influence do not outrun light, so every solid object is a kind of slowed down conversation between atoms, a conversation with a finite speaking speed. That's why you can never have a perfectly rigid sphere that guarantees instant response from tip to handle. That's why there's no perfectly rigid lever that acts everywhere at once. That's why rigid body mechanics works beautifully until it suddenly doesn't, because it was never a fundamental truth, only a convenient story told at low speeds and small sizes. And there's something oddly calming about that. It means the world is not held together by magic connections, it's held together by local rules applied relentlessly. Neighbor affects neighbor, field affects nearby field, cause has to travel. Even the hardest diamond is not a single thing. It's an agreement that takes time to spread. Now, one last zoom out. If the universe allowed perfect rigidity, then information could travel instantly through matter. And if information could travel instantly, the universe would not have a consistent causal structure. You couldn't reliably say this caused that. You couldn't build a stable logic of events. Physics would become a mess of contradictions depending on who's moving. So the fact that your table is not perfectly rigid is not a disappointment. It's a requirement for a coherent universe. The softness, however tiny, is what keeps time from collapsing into nonsense. So next time you lean on a wall and you feel that solid, stubborn resistance, remember what's actually happening. You are not touching a hard thing. You are triggering a chain reaction of electromagnetic forces and quantum restrictions, and the response is racing through the material as fast as it's allowed to race. Fast enough to feel immediate, slow enough to keep causality alive. If you want, we can go one step deeper after this. What speed of sound really means inside a lattice, why some materials transmit stress faster than others, and how shocks and fractures are basically failures of communication inside matter. Because once you stop believing in rigid objects, you start seeing the real world, not made of stuff, made of signals.